what is driverless AI? Driverless AI is an automated machine learning tool that is that we try and make as best as possible industry agnostic. So we have seen several major banks, retailers, as well as manufacturing companies and healthcare companies start to utilize this product to enable them to do more machine learning and more predictive analytics. So what do we deliver? One thing is the idea of talent. So we, as a company, employ several of the top 10 Kaggle Grandmasters in the world. And by utilizing their recipes, their methodologies, we are able to reduce the amount of time that it takes to generate a valuable model from months to sometimes days or hours. And we also provide the concept of trust. We have in every run of driverless AI automatic documentation that explains exactly what happens and why we took the steps that we did at any specific time. We have automatic visualization, which generate plots that are useful for understanding the shape of the data, understanding correlations between different columns, etc. And finally, we also have MLI, which is considered machine learning, or is machine learning interpretability. Machine learning interpretability is the ability to use other surrogate models and other algorithms to actually explain a much more complex model. And I kind of already discussed this slide, so I'm going to just move through this one and this one as well. But this is basically the same idea. What we're trying to give you is a concept of automatically doing several things that a standard data scientist would do. So automatically generating models, automatically providing interpretability of those models, automatically generating documentation and visualization. So that's just moving forward with that. So I do want to show you the tool. So I'm just only going to briefly talk about these things from a high level, but automatic visualization is a tool that you can use from the get-go. Basically, what you do is you bring in data, and we will do a in-depth search of the data to find the useful plots and the useful charts that could show you things like outliers, things like data maps or correlation graphs, and give it to you in a consumable manner where you can interact with the plot itself. You can use it to understand and visualize your data without actually having to generate plots, which can be a very painful process for those who have done it in the past. Now, this is moving forwards towards how we generate our experimentation, but accuracy is one of the things that can be very important to a model. Making sure that we are highly accurate or extremely good at predicting new data from a model is one of the most important parts about machine learning. And driverless AI has typically performed in the top 5% of Kaggle competitions throughout the world with the models that we've generated in sometimes hours or days. So just a quick understanding of driverless AI's standard workflow, but there's kind of several steps to the machine learning workflow that we try and take over. So the first part is something that kind of occurs outside of driverless AI, but it's the idea of integrating your data or aggregating your data into a machine learning usable format. So that step is what we call data integrations. That may mean querying 6 or 7 tables out of your SQL database and aggregating it into a CSV file or Parquet file or some form of static flat file that enables you to then perform feature engineering on it, or just training in any kind of machine learning platform. Once it's in that kind of static file or static table, you can driverless AI starts to take over. So the first thing we do is feature engineering. We actually do massive amounts of feature engineering in terms of generating new features for time series, new features related to interactions between different columns, so on and so forth. And then we train a new model. And every time we generate new features, we train a new model and score that model to make sure that the new features are either good or bad. And if the new features are useful, then we keep them for the final model. If they are not useful, then we actually drop them and then don't use them in the final model so that we're not wasting cycles on unnecessary features. And the last part is interpretability. So interpretability is one of those things that can be very polarizing for a lot of the folks outside of the machine learning world. Oftentimes, a customer may ask, why did you actually make this prediction for me? So in the case of, say, fraud, maybe a bank sends you a text message that says, this is that we received a transaction that we believe is fraud. It's very useful sometimes to have a reason explaining that we received a transaction and it was transacted in New York and you actually are in San Francisco. That would be a very good reason to send to a customer saying, this is why we think this is fraud. And it can help to build trust in your system, help build trust in your model. So without further ado, I want to go into a demo of driverless AI. And so I'm going to just escape out of here and move to this one. I hope everyone can see my screen now. Okay, I thought it was sharing my screen. Okay. So at this point, I'm going to just kind of redirect us to the driverless AI user interface. Now, before we get started here, there is a way to interact with this via Python. So those who want to do everything we're doing here programmatically can do so. Okay, so starting from where we left off with the original discussion about the machine learning workflow is, this is assuming that we have our data in some form of machine learning ready format. Now, the cool thing is that driverless AI has several different tools to ingest data. So that doesn't only mean downloading a static file from Amazon, which you can do simply by enabling your S3 connector via the configuration settings. And what this does is it basically allows you to browse through your S3 buckets that you have access to and import data on the fly. Now, the other options are actually that we do have a couple queryable databases. So that would include Google BigQuery, KDB+, which is a time series database. Quite a few of the large banks use this, and Snowflake. Snowflake is a cloud database provider. So basically what you can do is input several different arguments and then a select statement. And this will be what we actually create the table as. So as you can see, we actually have quite a bit of data already in here. So I'm not going to go out and add more data into our current server running. But just to kind of accentuate the idea is that there's a lot of ways to get your data in, and we're building more every day. Cool. So now let's move forward. So after you have your data in, and for now I'm going to do two examples, but the first one is going to be more IID data, so static data, no kind of idea of time. And so we're going to use this data set from Kaggle, which is a credit card data set predicting whether or not a user has will default on their payment in this succeeding month. So a couple new things that have come along with driverless AI is the ability to actually split your data intelligently. So what this means is that we give, you can optionally give a new name. So credit card split 1, and maybe credit card split 2. And then basically say what percentage of the split do I want to give. So in this case, I can do something like an 80-20 split, fairly common. And basically when I hit save, it will go ahead and split the file. And then you can actually see that I now have a first split, which has roughly 80% of my data, and another split that has roughly 20% of my data. So this is something that you can do if, for example, you didn't already have a test and train data set. You can actually generate one on the fly in driverless AI. So in this case, we actually have a test and train data set, so it's not quite as necessary. But if, for example, you didn't, this would be a way to generate one without having to split your data in, say, Spark or Pandas prior to actually ingesting it into driverless AI. So the next step is visualizations. So just to kind of reiterate, what we're doing here is all related to just the data. We haven't even gotten to the modeling part of this tool. And basically what you can do is go to visualize, and what driverless AI will do is actually create automatically plots related to the data. So you could get things like correlation scatter plots. And what this does is it says, okay, what are the values that are most highly correlated, and tell me the values and how they correlate with the values in the other column. So in this case, bill amount 1 and bill amount 2 are extremely correlated, or fairly highly correlated, and you can tell this by the blue dots. So as it almost looks like a 1-to-1 ratio. If you look at it carefully at, you know, roughly a bill amount of $200,000, you can also see that quite a bit of the data there is centered around that middle line, which is, so as bill amount 1 increases by 1, you will also see a relative increase generally of bill amount 2 for the same. Another thing that you can also look at is correlation graphs. Now this can look a little cluttered, but the nice thing is we can actually tune this a little bit to actually see only the correlations that you want to see. So if I set it back a little bit, these are the least correlated values. Or if I set it up a bit, I can see the most correlated values. So in this case, the column pay for and the column pay 5 are fairly highly correlated, as well as bill amount 3 and 4 and bill amount 1 and 2. On the flip side, you can take a look and see that there are some, like the marriage column and gender, are not very correlated, which is actually a good thing. We don't want to be seeing leakage, potentially, from having marriage be highly correlated to your gender. That would potentially be an introduction to leakage. Now, another thing that would be interesting is, for example, if default payment next month was actually extremely correlated with payment 2, you might actually want to drop that column for fear of introducing leakage. Because basically what this is saying is that payment 2 is a predictor of the actual prediction that you want to be making. So what is good about these graphs is the ability to actually just quickly visualize and understand your data. In this case, payment 2 could be a dangerous column to introduce into your model, in which case you may want to drop it. Otherwise, you can actually keep it and see what happens. You also will get things like outlier plots. Outlier plots are super useful, again, because they're able to tell you whether or not there are outliers in a specific column. And this is just based on the general trend of the column. So in this column, bill amount 5, you'll see that most of the data centered around 0 to about the 400,000 range. So you've got a couple that are up in the 900,000, 800,000 range. And you can actually click on the dot and scan through the row to actually understand the data better. Now, in this case, this is actually not a bad piece of data. It's just beyond the rest of the data in the sense that it's not centered around the same distribution. But this is actually a correct piece of data. It wasn't a technical or it wasn't a accidental input, or in the case of you know, some of the old methodologies of inputting data where say 9999 was actually null. This is not that case, is essentially what I'm trying to say. And you can do this for every single column. So you can see that there are a couple outliers on either end. I believe this would be a -1, or excuse me, -6900. So this could potentially be an issue because you're seeing that the bill amount is a negative number, right? So in this case, if a credit card company, you could potentially see a bill amount that's negative, but this basically is saying that someone paid roughly $69,000 more on his previous payment, and therefore the bill amount is actually negative. So this could potentially be an incorrect entry. Okay. So one thing to note is that these plots are automatically generated, which does mean that there will be different plots for different data depending on what the distributions are and things like that. Okay, so let's continue forwards a little bit. We're actually going to start now with some experimentation. So what that means is in the datasets tab, which is this one, you can click on each dataset and actually do predict. And what that will do is bring you into the experiments tab. Now, if you are in the experiments tab already, you can just simply create a new experiment and select the data that you wish to predict on or train on. Basically, the first thing and the only thing you really need is a training data set. You can provide optionally a test data set. And what Driverless will do with that test data set is use it for the final validation score. So while we are training, we use it as holdout. We do not use that data, and that data is reserved only for giving a final score to the final model to let you know that the data is good. Otherwise, we'll use the holdout data from each of the cross-validation splits to actually score your final model. Next, you just have to pick your target column. So in this case, as we were talking about originally, it's default payment next month. And what this will provide you with is a couple new tools at the bottom. For one, you can set this as a regression problem if you choose, but in this case, it is actually classification. So we'll use classification. If you did have GPUs on your machine, you can either choose to enable or disable GPUs. GPUs are not a requirement of Driverless AI, but they do help to improve the speed of the experiment. Now, probably the really interesting thing is these three dials right here, and they are accuracy, time, and interpretability. Now, accuracy is all of these dials are on a scale of 1 to 10. So basically, it's a relative value. It's how much do I prioritize accuracy? How much do I prioritize time? How much do I prioritize interpretability? And you can see in the left-hand side over here, if I increase accuracy up to 10, you'll get a more complex model. You will get a more complex cross-validation practice. And you will basically be asking for the most accurate model possible. Now, if you decrease it all the way, what you'll notice is now it's a single model, and we're allowing for algorithms that can potentially be less accurate. So GLMs are roughly linear versus XGBoost or LightGBM, which are tree-based models. And you also see that the validation split no longer uses cross-validation. We'll tune that back up a little bit. And discussing time is fairly straightforward, but it's just how much work do you want to be done? How many iterations do you want to have? And setting early stopping. So in the case of 10, you'll see that it allows for 50 iterations of non-improvement before early stopping. But if I set down time to 1, early stopping is disabled, and there are only 9 iterations performed by driverless AI. And finally, there's interpretability. Now, interpretability is kind of a inverse function. Essentially, what happens is as I increase interpretability, the amount of work that we can do for feature engineering decreases. So you'll take a look at 10 as interpretability, and you can only see things like frequency encoding, number encoding, one-hot encoding, and some minor text handling. However, if I decrease this to 1, what you'll notice is that now we're allowing for clustering, we're allowing for truncated SVD, we're allowing for interactions and much more complex feature engineering, which is typically harder to understand later on from a human brain, right? So, if you take a cluster, if I generate a cluster of, say, 10 clusters, then what's happening is that each row is kind of falling into one of those 10 clusters, and we don't 100% understand why one row would specifically fall into this cluster, except for the fact that it's kind of like all the other things that have fallen into that cluster as well. So once you've kind of decided on these, and I'm gonna go ahead and show you the expert settings first. Basically what the expert settings do is it enables you to kind of tune the experiment a little bit more than just via those 3 knobs. So you can require certain algorithms or turn them on. You can also set certain values, like whether or not to actually build the Python scoring pipeline after the model is completed, or build the Mojo scoring pipeline after the model is completed, etc. And there are several different settings which you can breeze through. Now it's time to launch the experiment. So when we launch, basically what it will do is bring you into the running experiment page. What this gives you is several different views of what's actually going on during the experiment. You will get things like, once it has created the first model, you'll start to get things like precision versus recall, lift and gains charts, KS charts, and you'll also be able to see your actual resource consumption, so CPU usage, memory usage, GPU usage, if you had GPUs enabled, as well as a ROC curve. So now what you'll soon be seeing is things, these little dots popping up on the left-hand side, as well as a validation score here, and then also a list of variable importance in the center page. So a quick description is basically the left-hand side is what is the most recent model's validation score, how it compares to the previous model, so you can actually highlight them and see them, and also what is the variable importance. So these are the top 14 variables, and you can start to see, even with just a couple iterations, that the frequency of this column, which is something that we've generated, or the frequency of payment 0, is something that are feature engineered, and you can see that you can identify that by the tag. So these are the original columns, and the tag's frequency is a tag which we've generated, and they're starting to pop up as some of the more important features inside the model. Now, I'm actually going to go to an already completed experiment just to kind of give you a little bit more information. But basically, you can see that now this is a completed experiment. What you can see here is that the weight of evidence of age, payment 0, payment 5, and payment 6 is actually the second most important value in this final model, this specific final model. And then we're also having other things like numeric to categorical target encoding, numeric to categorical weight of evidence, and also frequency, clusters, interactions. And these are all features that driverless AI generated from the original data set that you did not have to generate yourself. So assuming this is an okay model and you're happy with the performance, now I will say that we're not getting a ton of lift out of this one specifically because it is a fairly small data set. So what you'll notice is that with smaller data and also the type of data that was already in here, the amount of lift is relatively negligible just based on the data itself. But you can do a couple different things. You can download the experiment summary, which will have the automatic documentation. You can build the Mojo scoring pipeline, which is basically, it's called a memory optimized Java object. It's extremely good for real-time scoring, so low latency, single row scoring. You can also download, build and download the Python scoring pipeline, significantly better for batch predictions. You can also diagnose this model. So this is typically something that happens later on in the model lifecycle. So maybe a week down the line, you've created a new model, or you have new data. You can actually click on diagnose the new data, or sorry, diagnose this model with, say, another piece of data that's new data that just came in, and see how this model performs against the new data. So this is actually super useful for lifecycle management, essentially, in understanding why did this model get worse over time, which can be impactful to your production environment, right? I'm going to go ahead and click download for the experiment summary and unzip it. And I just want to kind of show it to you guys. So basically, the really cool thing about the experiment summary is this report.doc. It's an automatically generated document that actually will show you exactly what we did over the course of the experiment and why we did it. So you can see things like these are the settings that we chose. This is the environment under which it was running, version of driverless AI, what data was selected, so on and so forth. But the really cool stuff is further down to the bottom, and it's basically details of what we decided and what parameters we used for the models, things like that, which can be very useful later on, especially when you're trying to prove that this model is production ready, or maybe bring this to your executive as part of the explanation for why this model is useful. So just a quick overview, and then because I'm somewhat running out of time, I do want to kind of move forward to some of the other cool stuff. So now we're going to move towards MLI, so machine learning interpretability. So the first thing we're going to do is click interpret this model. Basically what this does is if there wasn't a model interpreted, if MLI hadn't already run on the experiment, it would give you a progress bar. In this case, we've already run MLI, so that's why it redirects you directly to the summary page for this model's machine learning interpretability run. So the first thing we're seeing is a summary. Basically, a lot of plain text as far as what did MLI choose to do. So we give you ideas of what experiment key is for MLI, what the driverless AI experiment attached associated to this machine learning interpretability path, what data set was used, so on and so forth. Then we'll see things like the DAI model summary. So this is just telling us what are the most important variables inside driverless AI. And then we get into something also very interesting, which is the surrogate model summary. So a simple list of the surrogate models and how well they performed against the actual model prediction. So this one thing to note about MLI is actually it does not train on the actual values of your trained data set. It's actually training on the predicted values coming out of the final model. So the massive difference is that you're not trying to train new models, you're trying to understand why a model did what it did. And that basically gives you these kind of performance metrics. So you can see the root mean square error between the test prediction, or sorry, the prediction out of the original model and out of the surrogate models themselves. So that's what you're seeing here. You can also see R2 values as well as the RMSE across the threefold cross-validation. So we're going to dive first into the surrogate models, then into the actual model interpretability of the driverless AI model. So the first thing we're going to talk about is K-Lime. So K-Lime is very interesting, but basically it's built off of LIME. LIME is linear interpretable model agnostic explanation. But basically what it's trying to do is generate a line, a linear model that approximates the the final model itself. So these are all actual values, all these white dots, and the yellow line that you see here is the linear model that was generated. So in this case, it's not a perfect one-to-one match. You can see that there's quite a bit of distribution. But what it can do, which is really interesting, is if we do pick one that was fairly close, we can see specific reason codes. And if you click on the dot itself, you can either highlight it or you can click on the dot itself and then go to the explanations tab. Now what this does is it actually tells you that in this specific row, so 19200, payment 0, which is a column, payment 6 and payment 3 had a positive effect on predicting default payment, and with these values, right? And these are and so payment 0 had a value of 3, payment 6 had a value of 5, and it attributed an increase in the probability of predicting default payment by this amount right here. You can also see that there were negative attributions, including the gender, the specific person's limit balance, and the specific person's payment amount at payment 1. And these attributed to a relatively small decrease in the probability that they would default. You can actually compare the two. So, you know, the smallest positive increase was 0.05, whereas the largest negative or the largest negative influence was 0.005. So you can kind of see that this person was highly likely to default on their payment. Okay, so moving forwards, the next thing is decision trees. Now, basically what we do is we build a single decision tree. This is kind of very useful for explaining. I'm going to actually make this full screen again. Very useful for kind of generally understanding the path that a specific user, in this case the same user, took, or globally what most users took. So you'll see one gray line coming down the right side of this decision tree, and it will change depending on the row number that you pick. Some people will have fall into different leaves. But essentially what this is saying is at the column pay 0, or at the value of pay 0, if you highlight this, you can actually see it. Because it had a value of 2, 3, 4, 5, 6, or 7, it actually, this specific customer took this specific path. And you can see that for each of these indicators. So in this case, at payment 3, this specific row had a value that was either, well, positive or not, or null, right? But the other cool thing is that you can see the fat yellow line passing down through here and into this, I believe it's this leaf right here. And what this is saying is this is what most users path they took. So in this case, most users had this specific path. They had a value of -1, -2, 0, 1, or null at payment 0. And so they actually took this path, and you can see that the leaves that they fall into are less likely to default. So globally, not as many people default on their credit payment, which is pretty understandable. That makes a lot of sense. This person, number 19200, actually was one of the fewer people who did default. Now, moving forwards, we're going to the random forest surrogate model. So the random forest surrogate model provides a couple different things. It provides feature importance. Now, if you'll notice, there are two sets of bars. One is the local feature importance, and the other one is the global feature importance. So in this case, what you're seeing is that things like age actually locally affected this customer more than globally. Globally, age was less of a factor. But other things like payment 5 for this customer also were more impactful than globally. So this is actually a really cool chart for understanding just what variables were super impactful. And you'll notice that none of these values here are actually generated by driverless AI. That's because the surrogate models are trained on the original features only. And this gives you kind of a better way of explaining, other than, well, the categorical to numeric target encoding of these two columns. And now you can probably understand that that gets fairly complex and a little less interpretable. So the next thing we're going to look at is partial dependency plots. Partial dependency plots basically are if I change the value at this specific column, how does it affect the model and the prediction? So what you're seeing, again, yellow is global and gray is local, but at this specific variable, pay 0, you can see that generally there wasn't a significant amount of effect of changing the variable up until the payment value became 2 or greater, at which point, if you had a payment value of 2, you actually had a fairly significant increase in the likelihood that you would default, and then it kind of tapered off from there. And you can see globally, there's actually less of an influence than locally for this specific customer. I feel bad picking on 19200, but they just happen to be the customer I picked. And you can do this for all the columns. So you can also take a look at continuous columns like their payment amount. And in this case, their first payment amount, even globally or locally, had a fairly minimal difference. And so it seems that regardless of how much you paid, it didn't globally affect your model in terms of increasing or decreasing the chance of you defaulting on this payment. And finally, there's loco plots. So loco plots, I'm actually going to delete this value here so we don't pick on that customer too much, but it gives you essentially a similar thing as feature importance, but the major difference is that you get positive and negative feature importance. So things like payment 0 were highly influential in increasing the likelihood of default, but things like payment 5 were actually more influential, but in decreasing the likelihood of default on payment. So these are interesting values to see that actually this would have been a very important feature. And if I click here, it's actually the 4th most important feature, but it's not actually a positively influential feature. It's actually a negatively influential feature, not from the context of good or bad, but from the likelihood of default. So that's just a quick run through of all of the surrogate models. So now we're going to quickly just go to the driverless AI models. And you will again get feature importance. Now the difference is because we're using the driverless AI models, you will also see the generated features by driverless AI. So actually, payment 0 is still the most important feature, but you're also seeing things like weight of evidence, numeric to categorical target encoding, frequency, and these are things that driverless AI generated, and they're the top 5 or 6 most important features. So the really cool thing moving past this is actually the Shapley values. Shapley values, similar to loco importance, gives you the positive and negative influence of these new values, including the feature generated values. So frequency of payment 0 actually had a high feature importance, but for negatively impacting the likelihood to default payment. Whereas payment 4 and the numeric to categorical target encoding of their limit balance plus payment 2 had a significantly more positive influence. And again, you can always get local values. So if I say pick person number 100, you can actually see the gray bars appear, and these are the local influences for this specific customer. So they may vary from the global influences, and this is useful for this specific customer, right? So that's a quick overview of MLI and a little bit of understanding that. Now, just before we get into questions, I'm going to briefly cover 2 things. One is the resources page. So this will give you things like the ability to download the Mojo runtime jar. This is so that you can actually run the Java application that uses the Mojo scoring pipeline here. Or you can download the Python client so that you can interact with Driverless AI Pythonically. Pretty straightforward there. And then the last thing is deployments. So we're slowly adding to this, but basically what this enables you to do is actually create automatic one-click deployments to things like AWS Lambda based on your experiment. So I have a completed experiment here. And once the final dashboard appears, actually, you know what? I'm going to go to another one just to save us some time. But basically what I can do is I can all right, okay. Sorry for the confusion, but I believe that we may have disabled deployment on this specific account. So sorry for the miscommunication here. But the long story short is that you can actually go from the experiments page to create a deployment of the model itself. I know. Sorry, I actually know what happened. Is that you have to build the Mojo pipeline first. So once you build the Mojo pipeline, that's actually what we are deploying into the deployments, which is, so if you don't have the Mojo pipeline, you won't actually see the deployments. But once you do, you will get the ability to do one-click deployments to things like EC2, to a local REST server, to AWS Lambda, and as long as you provided the proper credentials, you can actually get these things. So at this point, we have about 14 minutes left. So I would love to open the floor for kind of questions. And I will try and show you the button as soon as it appears.
Great. Thank you, Nick. We have some great questions in the chat window, and we'll try to get to most of them with time permitting. The first question is, where can I get details of the various transformations, pre-processing, and feature engineering performed? Though I see it in the tooltip under variable importance, I would like to access it for all variables and get a full rundown of each step involved.
Can you guys still see my screen?
Yeah.
Okay. So they are all available in our documentation. If anyone's curious, you can go directly to docs.h2o.ai, and that's where all our documentation is housed. And as you can see in the window, I'm actually just searching for feature transformations inside the search bar, and then just click on Driverless AI transformation. So this will give you kind of the plain text for what we're doing in each transformation. And another thing that you can actually take note of is that any transformations that we did employ in the final model will actually appear in your report.doc. It would be, let's see here, feature evolution, and you can actually see the explanations right here as well. So in this case, we didn't use all of them, which is the reason why you don't see all the feature transformations as you would here, but you can see them here. Or rather, you can see the ones that we employed here. Hope that answers that question.
Yes. Okay.
Sorry, I'm actually going to just mention one time. So after we've built the final Mojo pipeline, you can see the new button has appeared for deploy. And from here, we will be adding these features. So as you can see, they're non-interactive at the moment. We do have Amazon Lambda, though, and you basically can specify deployment names, keys, as necessary, what regions you want to deploy in, so on and so forth. And that will be how you deploy these things. Now, you can also use environment variables, so you don't actually have to type in the keys. That way, obviously, you don't type in plain text the keys that you want to use. Cool. Sorry to distract from that.
No worries. Okay, so next question is, how do I get model files, data pre-processing codes, test and train sample data, and details of each iteration? I only see the scores for first and last runs, especially for one of my multinomial classification problems.
Nice. All right, I'm actually going to ask to see that question. How do I get model files, data preprocessing codes, test and train sampled data, and details of each iteration? I only see scores for first and last runs, especially with one of my multinomial classification problems. So all of this stuff is typically inside the experiment summary. So you'll actually, if we dive a little bit deeper into the file structure, you can see things like, let me see if I can find it here, ensemble.txt, features or rig.txt, features.txt, things like that. And this will actually just give you a general summary of everything that's happened in driverless AI that we've logged. Another useful place to go is actually to trace. This is something that I like to look at a lot, and it may look a little gnarly to begin with, but basically what this is saying is at each iteration, what were we doing? So you can kind of see it generally separated by lines. So vertically, you can see that this is one iteration, this is another iteration, this is another iteration, and you can highlight each of the little blobs and see what it did and when it did it. So all kind of useful areas for understanding what's going on with driverless AI.
Okay, the next question is there a way for me to select algorithms and compare with driverless AI taking care of the tuning alone?
Yes. So I briefly breezed over it, so I'll just go back and talk about it just a tad bit more. But essentially, if we had selected some data set, and once we select the target column, we can go ahead and take a look at the expert settings. Now, inside the expert settings, you get significantly more flexibility to manipulate driverless AI's basic runtime procedure. So if you, for example, don't want to be using things like XGBoost or LightGBM, or you do want to use Tensorflow for NLP, you can kind of tune what models you're asking driverless AI to use right here. So you can even use algorithms like rule fit or FTRL, which is follow the regularized leader. And this also includes other things like whether or not we want to use a certain number of the original features, or whether or not we want to have a certain level of feature and interaction depth, things like that. You can actually tune quite a bit more than just the models itself, but this is one thing that you, if you do want to specifically turn on and off models, this is where you would go.
That about does it for the questions we received on our end. Okay, well, yeah, so that was the last question. I want to say thank you, Nick, for taking the time and doing a great presentation. Before we wrap up, I'd like to say thank you to everyone who joined us today. The presentation slides and recording will be made available on our BrightTalk channel. And for more information, please visit h2o.ai.